Lewis structure and molecular geometries lab. So we've already done a good chunk of this lab. You went through and you drew out all of your Lewis structures and tried to determine the polarity. So now what I want you to do is look through the beginning part of the chapter 10 videos, which goes through electron pair geometry, molecular geometry, and bond angles in a sketch, and actually how to determine the polarity of a specific atom and molecule. In chapter 9, we talk about the bonds, polar or nonpolar. In chapter 10, we talk about the molecule as a whole. So this section, I would wait to watch those videos to go through it. For today, what we're going to be talking about is the part we would do in lab, which after you made your structures, to go through and make the physical molecular models with the kit. So this is a molecular model kit. And there's a little cheat sheet on the top, if you can see it, which tells you that the white belongs to hydrogen, the black belongs to carbon, red belongs to oxygen, blue to nitrogen, green to chlorine, orange to bromine, purple to iodide. Now, when I show you what's inside, it looks something like this. So you have your red, and that's for oxygen. You have your black, that's for carbon, etc. Then you have these two types of bonds. You have a gray short bond, and then you have this longer gray bond, and then you have a purple bond. So we know that there's three types of bond that we'll see. We'll see a single bond, a double bond, and a triple bond. Now, in chapter 9, towards the end, we talked about bond lengths. Now, would it make sense for a single bond to have the long gray stick, essentially, or a double or a triple? A single bond, since a single bond is easier to break, it's a little bit longer. So then it makes sense for the single bond to be the longer bond, then the double bond to be the shorter bond, and since I don't have a shorter one than that, I'm going to designate the purple as my triple bond. So when you make these models, it's good to designate and figure out exactly what you have so that you're just making the structures as you go through. All right, so let's figure this out. So the first structure here, beryllium chloride. So I have beryllium. On my little cheat sheet, I don't have anything for beryllium, but I do have chlorine. Chlorine is supposed to be my green. So I take two of my chlorines and I have a single bond. So my two chlorines, my single bond, and I don't have a beryllium, but what I'm going to do is just pick one of these to be my beryllium. Which one do I want? It really doesn't matter. Let's do this one. I'm going to pick the gray to be my beryllium to show you that it's linear, right? Two electron groups and no lone pairs. This is a linear structure. Awesome. And I'm going to save this because I may have another linear structure that I can use for the same molecule. Now I have boron trichloride, a trigonal planar structure. Now, the reason it's trigonal planar, I have 1, 2, 3 electron groups, no lone pairs. So I don't have a structure for boron. I just need something with 3 possible openings, which is this one. And then again, I have chlorine, so 3 more greens. So then I take my chlorines and attach it. Boom, boom, boom. Note you may run out here and there, and then you won't be able to save all of your structures, and then you just remake them from the beginning. I'm actually running out of single bonds already. So then, here is my trigonal planar structure for boron trichloride. Then I have my carbon, hydrogen, and chlorine organic compound. So I need a carbon, which I know I have. I have a black for carbon. And now I actually need to steal some of my single bonds from the structure before. So I have my single bonds for my carbon, which have a hydrogen on it. Boom. Another one, and then need one more. Awesome. So I have my carbon, my 2 hydrogens. Now I need my chlorines. And now you can see the tetrahedral arrangement. Central atom, 4 electron groups around, no lone pairs, all 109 degrees from one another. Then we have ammonia. Now this is a trigonal planar. Now this ammonia is with nitrogen, which is blue, and it has 3 hydrogens around. So I'm going to take them from my last structure, just because I'm running out of single bonds here. And then you can designate one of these extra white things to represent your lone pair. So you have your nitrogen with the 3 bonds, and then the lone pair on the top that causes the angles to push the bonds down through the extra repulsion of the lone pair. Then we have the water, which I already made from the other video. You have the oxygen with the 2 bonds and 2 invisible lone pairs on the top. Now we have another trigonal planar shape, oxygen, and then 3 hydrogens around. So the oxygens that I have to use is the one that has more than 2. So there's 2 forms. You have one with 4 options to make bonds and one with only 2. Since hydronium ion has 3 hydrogens, I need the one that has the option of 3. Boom, boom, boom. Almost done. I have my 3 bonds. Now I want my lone pair. And now you can see that the lone pair at the top forces my bonds to a lower angle, creating a trigonal pyramidal shape. 1, 2, 3, 4 electron groups, tetrahedral, but the lone pair makes it trigonal pyramidal. Now I have carbon dioxide. Carbon dioxide is linear. So I need my linear submolecule. Where's my... I had one. Perfect. So I'm just going to use the same for my linear. I'm saying this is my carbon, and then this is my oxygen. The difference, though, is instead of a single bond, I have a double bond. So I'm going to use the ones that I designated for double bonds with the oxygens to give my linear substance. Carbon and dioxide to give you the 2 double bonds here for a linear geometry. Now I have sulfur dioxide. So if I go back to my cheat sheet, my color for sulfur is not given. So I'm going to make it be the oxygen since they both can only make 2 bonds. One will be a double bond with a oxygen. And then one will be a single bond with an oxygen. And then I have a lone pair at the top. So it would look something like this, and then the resonance would just be the opposite structure. You have the double bond, the single bond, both are red because we have the sulfur, and then the 2 oxygens, and then the lone pair. Then we have our methane oxygen over here. So I have a tetrahedral geometry and then a bent geometry. So if I go back to my carbon and I make my 3 hydrogens bond, and then I need a bond, another single bond for the oxygen, and then that oxygen has a lone pair, 2 lone pairs, and then it bonds to a hydrogen. And then it'll look like this. So very different than what you can see planar. You can see that you have your tetrahedral geometry for the carbon and the bent geometry for the oxygen because of the lone pair. Then we have dicarbon hexahydride. So I need 2 carbons now. And then I need, I don't know if I have enough. Oh no, I think I do. 6 hydrogens. Both of these are completely symmetric. Both, if you cut this in half, they're like mirror images of each other where they both are a tetrahedral geometry. Then we have carbon and hydrogen, but we have a triple bond. So I already decided that my triple bond will be represented by my purple bond here. And then I only have one hydrogen left. So I will get something like this, a linear shape. Now this should be a little bit more linear than it looks. So it's more like this. Ugh. Take some time to put these apart over and over again. There we go. Carbon, carbon. Then your hydrogen. Ugh. Boom. There we go. That looks way better. You have your triple bond and then the single bonds with hydrogen, linear geometry. Alrighty. 2 more pages. Almost there. So then, now we have a H2O2. So we have the oxygen that's bent in the middle, and then we have the hydrogens on the outside. So we have the oxygen and the oxygen, and those oxygens are attached to hydrogens. And they both have lone pairs on the outside. So you can see that because of the lone pairs, this is not linear. This creates a bent structure. Then we have another tetrahedral arrangement for sulfate. So you take your, boom, boom, boom. Just take this one. I'm going to make the oxygens just be the white this time so we don't get confused. Just to show you what tetrahedral will look like. However, I have 2 double bonds. So, something like this. So here I have tetrahedral, but I have my 2 single bonds and then my 2 double bonds. These I'm saying are my oxygens, and my middle is my sulfur for sulfate. Then I have my isomer. So an isomer is when you have a mirror image where the atoms will actually move instead of the bonds. So the first one is when you would have the bromines on one side and the hydrogens on the other. And the second is when you have the bromines on opposite sides of one another and the hydrogens on the opposite side. So for bromine, my color is orange. And I actually have orange. So I need my carbon. Then I have hydrogen and hydrogen. And then my bromine and my other bromine. So you can see here that's one isomer when the 2 bromines are next to each other. And then my other would be, you would think if I moved it, however, 3-dimensionally it's exactly the same. 2-dimensionally we would just draw it opposite, the bromines on the opposite side, where here they were on the same side. But here you can see the carbon, all single bonded to the hydrogens and the bromines. Then we have another linear structure. So we have carbon triple bonded to the nitrogen, which is bonded to sulfur, singly bonded to sulfur. And that'll look like this. Carbon, triple bond to nitrogen, single bond to sulfur for a linear structure. Then we have phosphorus. Phosphorus is not on the chart, so we might not be able to make this because I need to be able to make 5. 1, 2, 3, 4, 5. Great, I can use this. So phosphorus with fluorine. So I'll just designate the white to be the fluorines, just for teaching purposes so you can actually see it. Now you can see a trigonal bipyramidal structure. You have the phosphorus in the middle. I'm designating that to be phosphorus. 1, 2, 3, 4, 5. Bonding groups, no lone pairs. Trigonal bipyramidal. And then we have sulfur tetrafluoride, 1, 2, 3, 4, 5, 5 electron groups, but one of them will be a lone pair. So I'm going to use the structure again, but I'm going to make one of the bonds a lone pair to give me my seesaw shape. So now you can see the seesaw shape. So still 5 groups total, 1 is electron group, and then 4 bonds. Last one. BRF3, so bromine trifluoride, 1, 2, 3, 4, 5 groups. So we again have 5 groups, this time 2 lone pairs and 3 bonds to give us a T-shaped. So you can kind of see how it makes a T. Then we have xenon trifluoride. Now I do not have one that makes a 6 bonds, but I can use my linear structure from before. With the single bonds of the fluorine, and we know that there's 2 lone pairs at the top and 1 at the bottom that give this a linear structure since it's octahedral. Then I have another octahedral substance, sulfur hexafluoride. We don't have one that can make 6. 1, 2, 3, 4, 5. Oh, I do have one that can make 6. Just found it. So sulfur with 6 fluorines is an octahedral and looks like this. Oop, I need one more. Oh. Boom, boom, boom. There we go. 6. Octahedral. 1, 2, 3, 4, 5, 6 electron groups, no bonds to give us our octahedral shape. Oops. Then we have 1, 2, 3, 4, 5, 6, another octahedral for iodide pentafluoride, but with a lone pair. So then I take one of those bonds, give it a lone pair to give me my electron geometry for when I have 5 bonds and a lone pair that pushes the bonds down like this, almost makes it look like a square planar seesaw shape. Last one, we have 1, 2, 3, 4, 5. So I will use the one that I had for my 5. So that'll say that's bromide. And then my white will be my fluorine. And then you can see that makes another seesaw shape when you have the lone pair and the 4 bonds. The lone pair repulses the electrons further down, creating those angles. And that's the Lewis lab structure. So you should go through and check your Lewis dot structures, check if you have any resonance. Now you've seen what they would look like 3-dimensionally. I know I went a little bit fast, so feel free to rewind and pause. Knowing how to use these kits was what's important. Now go through the chapter 10 and fill out the rest of the worksheet before you have to turn it in next week.